Hi guys, it's your guy Olumide. Today we'll be solving another one of the most commonly asked tech interview question, the maximum sum of a continuous part in a binary tree. It's a DSA problem that is most commonly asked in top tech companies like Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that return the maximum sum of a continuous part in a binary tree. A part is defined by the following characteristics. The first characteristic is that a part consists of a sequence of nodes that can begin and end at any node in the tree. A sequence of nodes that can begin and end at any node in the tree. Each consecutive pair of nodes in the sequence is connected by an edge, right? And then the part must be a single continuous sequence of nodes that doesn't split into multiple parts. So, and then the problem statement is just wanting us to return the maximum sum of a continuous part in a binary tree, given that a part is defined by this tree definition. First, it consists of sequence of nodes that can begin and end at any node in the tree, and then each consecutive pair of nodes in the sequence that form the part should be connected by an edge. This is what we call an edge, and then the part must be a single continuous. It must not break into several parts. It must just be a single part, meaning that a single line or track. Okay, so we are giving this example tree here, the binary tree, and then since we have to return the maximum sum of a continuous part in a binary tree, so we see that this is a part. Actually, we can extract a lot of parts from this particular tree. We can this 11 alone is a part on its own. 1 and 11 is a part. Minus 10, 1, 11 is a part. So there are several parts. 11, 10, 11, 1, minus 10, 7, minus 1 is another part entirely. So, but if we are actually asked to return the maximum sum of the continuous part, meaning that we want to find the part with the maximum sum of values, and we can see that this part actually evaluates the maximum sum that consists of 9876. When we sum it up, you'll see that it gives us 30. It sums up to 30, right? So if we consider another part here, you see that it won't give us up to that, right? Now we'll be explaining logically and solving how to come and then how to solve this problem and come at the desired output. So the constraint that is given to us is that the tree contains at least one node. Now the first thing to understand that we need to understand in solving this problem is actually what a part is in a binary tree. What do we call a part in a binary tree? Let's consider this binary tree here. One thing is that every part that exists in this binary tree, which can actually start at any node and end at any node in the binary tree, actually have a root node. Every part in the binary tree have a root node. Consider this part now that consists of these two nodes, minus 10 and minus 7. So the root node is going to be minus 10. Consider this part now also, this second one here, that is actually a part from from this 11 straight here. You see that it is actually a single continuous sequence of nodes, right, that are connected by edges, because you see my 11 1 minus 10 5 8 7 3. So it actually doesn't split into two if you take it in the right part, right? And we can see that the root of this part is 5. So root is actually what kind of navigates into that particular part. Considering this one too, now look at this single part also that comes from 9 8 7 and 6. You see that the root of the part is 8. So every part have a root. So just as our binary tree have a root, which is root 5, every part that we can extract from this binary tree at all also have their corresponding roots. And when I say root, I mean root node. This can also simply means that every node that we encounter in this binary tree is a root to a particular part. If every part can have a root, and this node 11 itself can be a single part, fine here, because it's actually it is a node. in the tree. So it could be it could be a path on its own. So 1 and 11 could also be a path, minus 10, 1, 11 could be a path. Any form of sequence of node that could be joined together by an edge could be a path. And definitely, if every path should have a root node, then definitely every node in the binary tree is also a root node to a particular path. Look at this node 8 now, is the root node to this path, that is highlighted in the red ink. For example, now let's consider node 7. We can see that node 7 is the root of 4 paths, and this is the first path here, which is actually node 7 itself, is a path on its own, a valid path on its own. Node 7 down to node 6 is another path, and if you look at this path, look at their sum. For the node 7, the sum is 7. For node 7 down to 6, 7 and 6 gives us 13, the sum up to 13. And then looking at this third path, starting from node 7, I mean third path with node 7 being the root of the path. The sum here is 4, which is 7 minus 3. And look at the fourth path, which actually combines 6, 7 and 8. So in this direction, so you see that it's in this direction like this, from 6 to 7 to minus 3, and the root node is still 7. So, and here the sum is actually 10. The sum of the nodes values in this part is 10. 7 plus 6 minus 3 gives us 10. And so I'm just trying to say that node 7 in this particular tree actually have 4 parts in which it is the root node. I mean, node 7 is the root node of these 4 parts, and then we can see the sum of the sum part, or let me say the sum of the nodes at this particular part. Now, what this observation actually tells us, and try to open our eyes to, is that considering every root node, right? Every root node of every part. Let me say that since we have concluded that every node in the binary tree is a path to, or let me say is a root node to a particular path. So just like now, as we highlighted 7 now, 7 is a root node to, in fact, 4 paths, right? So now to find the maximum sum paths, I mean the path with the maximum sum, all we need to do is to consider each and every node in the binary tree, right? And for each and every node, we consider all possible paths that particular node is a root node to. Just like this case of 7, whereby 7 is actually a root node to 4 paths. Now we just have to find the maximum of the sum, the maximum sum that we can encounter, and we will do that for each and every node. Fine, we know that for this particular node 7 now, having 4 parts, the maximum sum part is 13. Now we are going to do that and repeat it for other nodes, so as to evaluate the maximum sum parts that we can get from any root node in the binary tree. Now let's try calculating the maximum part sum at any node. So considering the root node of our example binary tree, the maximum sum of a path rooting from node 5, I mean the maximum sum of a path whereby node 5 is the root node in that path, involves the maximum gain that we can have from the left subtree and from the right subtree of the node 5. And what I'm trying to say is that the maximum path sum rooting from node 5 is just equals to 5 plus maximum from the left. So, and what I mean by maximum from the left is the maximum path from the left, right? I mean the maximum sum part that we can obtain from this left subtree, plus the maximum sum part that we can obtain from this right subtree, and plus 5 itself. Why? Because 5 also constitutes, I mean node 5 constitutes in the parts that we are trying to create. So, and because of that, we'll be having the maximum sum part to be 5 plus the maximum part from the left and the maximum from the right. Now let's consider what happens, and let's evaluate the maximum sum part that will be returned from the left and right subtrees. So from the left subtree, this is the maximum parts. You see that we have 2 parts that we can take here, the one of 11, 1, 10, minus 10, or we can decide to go for minus 1, minus 7, and minus 10, right? So we see that 11, 1, minus 10 is going to evaluate 2. 11 plus 1 gives us 12, 12 minus 10 gives us 2. So comparing that with minus 1, minus 7 and 10 is actually minus 1, minus 7 and minus 10 is actually a negative part, right? It's going to give us a negative sum. That is going to be minus 18. So comparing minus 18 to 2, we see that this part that we choose here in this region, in this red region, is actually the maximum part from the left. Considering the right too, just taking note of the right, you will see that the maximum part is already highlighted also in the red, in this red region, because we see that this is a part starting from 9 to 8 to 7 to 6, and that's sum up to 30, right? So this is the maximum part we can achieve from the right also. So now summing them up right here to give us 5 plus 2 plus 30, we make up 37, right? Yeah. But we can see that from this structure here, I mean, it's still the same structure as this particular one. You see that the branches are the same, the region is the same, but one thing we notice is that this is not the real part. Why? Because when we get to this particular node, I mean this node here, this node that branches into this and this two node here. So when we get here, we see that it branches into 2 parts. You understand? When we make the recursive call, when we make the recursive call to this node 8, this particular node 8, actually it branches into 2 nodes instead of, unlike here whereby the node is just 1, right? So look, I mean the path is just 1, but here it branches into 2 nodes. Look, one is from 9 to 8, and then from 8 to 7 to 6. So you see that from here, look, now considering the whole part, look at this part that move from here to here to here, then to here, then to here. You see that it has now branched to 2 nodes at this particular point, at that particular node 8. At this particular node 8 here. Why? Because there's no way we want to follow a continuous path from this node here down to this root node, and is either we choose to go this way or we choose to go this way. So this is not a valid path because it breaks into multiple branches when we made the recursive call to node 8. I mean to calculate this maximum part of the right subtree. So it branches into 2 parts. But here we can see what we actually want, because now the path is not divided into multiple track, unlike in this previous one here. It is just one. We selected one instead of having to select 9, 8, 7 and 6. So we select one here. So, and that way we see that the sum of the continuous parts actually give us what we wanted. It gives us a valid path because look, now we are able to trace it continuously along a single path, right? And this actually sum up to 5 plus 2 plus 21. So don't forget that previously it sums up to 30. This one sums up to 30 instead of 21, because we included 9. We perform multiple track here, 2 tracks, so which is not supposed to be. But right here now we just include 8, 7 and 6, and the sum is 21, and we see that that is correct. So we can conclude that the difference between the valid and the invalid part lies in the difference in part that is returned by the recursive call to node 8. This particular node 8 here, this particular node 8, you see that for the invalid one, when we call it, it actually returns a path that branches into, that has 2 branches, while when we call it here, is the call actually return a single and continuous path. So we can see it right here visually that in this live diagram right here, an invalid path is formed at this particular node 5, because at node 8, right here at node 8, we return the maximum path sum, which is from a path with 2 branches. Look at this node 8 now. You see that it's actually from a path with 2 branches, but in the right diagram now, a valid path is actually formed because we are not actually interested in just the maximum path sum at the particular node 8, but we are interested in the largest sum path, maximum sum path with a single branch, with an emphasis on a single branch. So we are not just considering anyhow path sum, but we are trying to ensure that it actually is formed from a single branch. Now let's see how to identify the value that we return during the recursion. So let's consider this same previous node 8 that we are talking about previously. We see that fine, at node 8 the maximum sum path, this is a valid path, right? Consider taking a line, taking this path 9 to 8 to 7 to 6. It's actually a single path, but we are not just considering the maximum sum path. It has to align with their parent, with the root node, or with their kind of root node, right? So we are not just returning it. We actually are interested in returning a single continuous path. So we can either have the option of returning this single path of node 9 to node 8. Why? Because it is single, right? Or returning node 8, 7 and 6, right? Because it's also a single one. So if I were to return this path now, what we are going to be having is actually 17. 9 plus 8 is 17. Is going to be the sum of this part here, while the sum part for this one is going to be 21. So now definitely that means that we'll be returning node dot value plus maximum between the left sum and the right sum, so as to come across the largest sum parts in a single track. Don't forget that this left sum is given by option 1 here, 8 to 9, right? 9 to 8, while this right sum is given by 6 to 7 to 8, right? So in order to avoid returning the sum part for a multiple track, in order to avoid that, what we want to do is that we want to return the maximum between the left or the right sum part, right? So that way we can always ensure that the maximum is what we are returning, and at the same time we are returning a single track, a single part. So, and why we are adding node dot value to it right here this way, that you can see node dot value, is because the node itself also form the part, right? So we have to sum it up and return it to node 5 that way. Now that we are getting the single continuous path sum from the left and right subtree, right? Look at in this situation now, we try to consider the left subtree by checking for the left sum, and the right subtree by checking for the right sum and finding their maximum. So we can only choose one out of those sum parts, so as to get just a single track. Now to calculate the maximum path sum routing from a node, now will be given by this, by node dot value plus left sum plus right sum. Don't get it confused. Let me copy it right here. Don't get it confused, because you might be thinking that, oh, but we said we don't want to get we don't want to find and keep track of two things. We don't have to we are trying to choose the maximum between the left and right so that we can go for one, right? I understand, but that is to avoid getting into two track, right? That is to avoid getting the sum part from two parts or two tracks, right? But then to find the maximum sum routing from a node, say that from this node now, this particular node 8, so we actually are going to add the left sum with the right sum with the node value so that we can get the maximum. Don't forget what I said earlier, that even this part 9 to 8 to 7 to 6 is actually a single part, right? Is a single part. But considering the fact that we are taking our root nodes to be node 5 for instance now, whereby the part is already approaching from the left, just like in this case, whereby the part is already approaching from the left here, right? So because it is approaching from the right here, if we divide into two, just like here, let me this place now exactly, whereby it's already approaching from here to here to here, and then it now divides, so that now there's a part, there's a problem here Why? Because it is divided. There's no how you want to take the motion from here down here and come here and still go back again to this point and come here again, right? You understand? But that's why we have to choose the maximum between the left and right at this particular node. But imagine if this particular node itself, I mean this node 8, that node 8, imagine if it is actually the root node. We might want to check the maximum sum rooting at that particular node, and at that particular node now, this path is actually correct. Imagine we are not taking this path any longer. Simply imagine we are not taking this long path any longer, and the whole path we want to take is this single one here. You understand? This 9 to 8 to 7 to 6. You know, it's very fine to sum up everything here and to return it here because it's a single path. So even as much as we are treating the node 8 as a left subtree or a right subtree and making sure that it doesn't divide into multiple tracks, we also are gonna divide a different variable that is gonna keep track of the fact that, okay, what if it is this particular node 8? What if this is the node or let me say, what if this is the root node with the maximum sum path? So it's two things we are doing. Fine, we are gonna just return one thing we are going to do is that we are in our recursive call to this node 8. Don't forget we are going to be performing recursive call on each and every node and treating each and every node as a root node. On the recursive call to each and every node now, we are going to return from that call. Fine, we are going to return. So what we are going to be returning is just the sum part for a single track. Why? Because in returning the sum part for a single track, node 5 will be able to use that single track sum part for its own. You understand? So we're gonna be returning that, and as we are returning that, we are also gonna keep track. This one is different from the return statement now. It's just keeping track of the maximum sum at each node, maximum sort part. So, and that can be gotten by summing the left and the right with the node value. So that's how we'll be solving this problem. Two things: we are going to be treating it as a left subtree and a right subtree independently, and making sure that at that point we are returning just a single track. I mean just a single track, a sum part for a single track. And we are also going to be treating it like it might be the maximum sub part. That node might be the node we're actually interested in. So that way we're going to sum the left and right and the node itself. So you are going to understand more in the code implementation in which we are going to be going into now. Alright, let's go to the code implementation for the maximum sum of a continuous path in the binary tree DSA problem, right? Okay. First of all, we'll be having our tree class, right? We'll be having our tree node class, which actually represents the node that we'll be using. Just like you can see on the visual diagram on the screen, you know, we will be representing each of the nodes using a tree node class. Also, we will be defining the nodes. So these are nodes that you can see on the screen. Actually, you know, we have the node 5 connected to let me check. We have node 5 connected to node -10 and node 8, and that corresponds to node 5, node -10, node 8. So all of this node that we'll be needing, just like it is drawn on the screen, is what I try to define here. And I try to define them, and actually I'm trying to be snappy because of I've used a lot of time, and I'm sorry for that. Okay. Similarly, now these are the connections between the node. So we have node 5 left child to be node -10 and node 5 right child to be node 8, and that's why you are seeing node 5 dot left comma node 5 dot right equals to node -10 and node 8. So, and the same applies to others like that. Like now node -10, that node -10 have a left and right of node 1 and node -9 respectively. Okay, so what we're going to be doing now is that I'm gonna be printing. I'm trying to call a function now. So although I've not defined it, but what I'm trying to do in essence is that I'm trying to call the function that will help us to determine the maximum sum of the continuous paths in a tree, and then I'm passing in the root node, which is node 5. So you can see that on the screen now. There's the tree actually have a root node of node 5. So now let's define the function. The function is the maximum sum, right? So it's going to be taking in a node, which is actually the tree node, is actually a tree node, right? And then the return is going to be an integer, right? So fine, we'll be calling a function here. So first of all, let's define a variable, so maximum sum, that is going to help us to keep track of the maximum sum at each node. So let's set it to 0. Don't forget, there are two things that we'll be needing: the maximum sum at each node, because each node could be a potential root node for the maximum path sum. I mean the path with the maximum sum. So that node could be each node could be a potential root node in the tree. So that's how I'm dividing the maximum sum, to keep track of the maximum sum at each, I mean the maximum path sum at each node. So okay, so let's define it as global. We'll be needing it here, maximum sum. So right, and then let's call this function, we call it the mass, what do I call it, maximum mass sum part. Let's call it the maximum sum part. So this function will be the recursive function that will be calling each node, right? Recursive call to each node. So we'll be passing the root node there at first, and then we want to believe that by the time the whole node has been looped, we will definitely be able to track down the maximum sum so far, so we can then return it. So you see what I just did there, I defined the maximum sum as 0. I made this global so that I can amend it and I can use it in this particular function, or otherwise it will be local. So I have to define it as global so it is amendable and usable, referenceable in this function. And after doing that, after defining it as global, I try to call the maximum sum part, right? So on node, and after that I return. So believing that the maximum sum part is actually going to be a recursive call to each node, and as we are trying to recursively call each node, we are going to be checking if that node is the maximum sum. So we're going to be keeping track of the maximum sum. After the node has been successfully called, we can now return the maximum sum so far. So let's define the maximum sum track then, sum part, sorry. So the sum part is going to get a node, which is going to be a tree node, right? A tree node. So, and then the value could be well, I have no idea what the value is right now, but we will get to know about it more. I mean the return value, right? So now what we want to do is that if not node, so it's going to be recursive, and then there needs to be a way whereby we will stop the recursion. So, and that's if we have gotten to a non-node. In fact, I won't call it a non-node, it's just none, because when we get to a leaf node, it means that the last node in the last set of node in the binary tree, the left attribute and right attribute of such a node will be none, right? And for a none, we just want to return 0. Why? Because the maximum sum part at that time is 0. So let's conclude that we'll be returning an integer, right? So it's going to be an integer. So if not known, return 0, because when the node is none, then the maximum sum part at that point is 0. Okay, fine. If it is not known, we want to find the left sum, the maximum sum part to the left of that particular node. So it will have a left attribute and a right attribute, and we can do that by just calling maximum sum part, the function on node dot left, right? So, and similarly we are gonna do for the right sum as well, and we're gonna do that by calling it the maximum sum part on node dot right. So with the hope that it will return a sum for us, so the left sum part and the right sum part. So, and what we want to do is that we want to set the maximum sum. So don't forget, the maximum sum is the variable we define up here, so right here. So we have to define it as global here, so we can use it also here, global maximum sum, right? Fine, we define it as global. Now we want to keep track of the maximum sum at each node. Don't forget, this is actually a recursive call to each of the node. So at this particular node, we want to keep track by finding the maximum between the existing maximum sum, which is already there, for a particular node before, and then the new one, so which is going to be node dot value, I mean for this particular current node, plus left sum plus right sum, right? So, and what this means is that the sum part at this particular node, taking this particular node to be the root node, now we want to sum the left sum part plus the right sum part plus this particular node itself. So if it is greater than the existing maximum sum, I mean the existing variable, we want to then update that existing variable. So, and we want to return at the end of the day, we want to return the node dot value plus maximum between the left sum and the right sum. So, and why we are doing this return is because we actually want to keep track of the single continuous sum part for this particular node, so that we can evaluate the maximum sum part for its root node, I mean for its parent node. So by doing the same thing, so as we can see here, 30 is returned, and as you can see, this is 30 is returned here, so which is actually the answer if we consider the code that was actually given to us. So you see that the output is 30 here. So the output is 30, just like you can see on the code here. So that's how to solve this problem, and I really hope you understand this. Kindly do all to like, comment and subscribe to my YouTube channel. Thank you.